everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. In today's topic, we will see triangular, tetrahedral, quadrilateral, and hexahedral cells. So basically, what are these cells? Why do we use actually? And what is the significance of these cells? And how does the solution of computational aerodynamics will vary when you change these aspects of the cells actually. So this is very important. So let's see. So first foremost thing, so when we come to a mesh or grid, so we have actually different sets of cells. So basically cell is the smallest entity of the grid. So here this diagram you can see clearly the cell. So here this is the center of the cell, okay, and the boundaries of the cell. So here you can see this is the y boundary and this is the x boundary. So these two are perpendicular to each other, and you can see the lines. So basically here this is called x is equal to 1 line, here this is called x is equal to 2 line, here this is called x is equal to 3 line, here this is called x is equal to 4 line. So this one, let us take y is equal to 1 line, so y is equal to 2 line, y is equal to 3 line, so y is equal to 4 line, so y is equal to 5 line. So basically how many grid lines we have along x-axis? So along x-axis we have 4 grid lines actually, and along y-axis we have 5 grid lines. So here you can see the x1, x2, x3, x4. So no two grid lines are meeting each other. So if you go on till infinite, so here you can see this grid line, this one 4 and 3 are not at all meeting together actually. So when they meet together, then that sort of grid is called unstructured mesh. So this is basically called a structured mesh. Okay, so this one basically, so this one is called a structured mesh, and when these grid lines, so x4, let's say x3, when they are meeting each other, so then that sort of grid is called the unstructured mesh. So we'll see in detail, but currently you see, so what is the significance of a cell? So basically this cell will capture the data of the flow. Okay, so we have different types of flow. The flow is compressible, incompressible, so inviscid, viscous, and so fluid if you take, so you have air, water, and Newtonian fluids. So when you have non-Newtonian fluids, so you can take glycerin, and we can take honey. So these are of non-Newtonian fluids. So whatever the fluid you take, whether it is a non-Newtonian fluid or Newtonian fluid, to capture the physics of the flow, the cell is required. And to draw the cell, so what are the basic entities we have? So we have x grid lines, we have y grid lines. So when x and y grid line is actually are meeting together, and if they are perpendicular, let's say if it is of 90 degrees, so then they are called perfect structured mesh actually. So even you have like a cells which is adapted to body, so you have a parallelogram kind of thing, or this is also called quadrilateral. So where this can also have an angle, let's say some 40 degrees, or this angle, let's say it is of 60 degrees, or let's say 70 or 80. So it's not actually equivalent to 90 degrees. So it's not mandatory to have 90 degrees every time for a structured mesh. So when you deviate from the 90 degrees, so basically the lines angle between two lines, let's say x line and y line, so if the angle is 90 degrees, so we say it is orthogonal actually. So now what is happening? So when the mesh is deviating away from the orthogonality, so mesh deviating from away from orthogonality in the sense, so for example, we have a curved bump actually. Let's say you have a curved bump. So we have a curved bump. Okay. So if you are doing mesh here, so what happens actually? Here you have a grid line like this. Here you have grid line like this. Here. So somewhere, so like what happens? So the Y lines will adapt to this lines. Okay, they become curved nature actually. So it need not to have uh, an angle of every time 90 degrees between these X lines and Y lines. So between these X lines and Y lines, it need not to have every time 90 degrees. Okay, so when it has 90 degrees, so basically it is non-orthogonal. So sorry, orthogonal. So here this is non-ortho. So basically what happens actually, so when we say it is a non-ortho, so in the case of non-ortho, what happens actually? So it deviates. So it is deviating from the 90 degrees. So we need to measure how much percentage of non-orthogonality is present in the mesh. So that we need to calculate, and then it will account for the realistic results actually. Fine. So here we can see, so the finite volume method is mostly suitable for the complex geometries. So let's say you take simple geometry or you take complex geometry. So whatever the geometry it is, the mesh can be structured or unstructured. So and one more type of mesh which is called hybrid mesh. So hybrid mesh in the sense, so it is the combination of structured and unstructured mesh. Okay, so here, so meanwhile first let's see what is triangle and hexahedral and quadrilateral, and so these cells we'll see. So here, as I told you, we have two types of mesh. So first one is a structured mesh. Okay, so we take this. So this is called a structured mesh. Now we can draw the same entity in unstructured mesh. So we have unstructured mesh. So here what happens actually? So they don't form 90 degrees. So let's say you have like this. So you have element like this. So we have element like this. Okay. So we have an element like this. Okay. Like this. So here what is happening actually? So every time if you see these elements, whatever it has formed, they are of basic triangular units. Okay, so here what is happening actually, you can see clearly. So let's say he has how many cells? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 cells. Let's count the cells here. So we have, let's say, we start numbering from here: 1, 2, 3, 4, 5, 6, 7, it's 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 cells. So you can see here the difference you see here in a structured mesh, for the same, let's say we have the same dimension which is of 1 meter cross 1 meter. So here let us take these of same dimension of 1 meter cross 1 meter. So for this domain, so basically this outer edges, so outer edges in the sense, let's say this is edge A, this is edge B, this is edge C, and this is edge D actually. Okay, so same again, you have edge A and edge B and edge C and edge D. Okay, so edges A comma B comma C comma D. So when you combine these edges A comma B comma C comma D, then it form a domain. So basically, domain is nothing but it is an entity where the whatever the fluid flow or whatever the heat transfer that will take place will the process happens inside the domain. Okay, so outside the domain, so there is nothing the flow. Okay, so there is no flow which is present outside the domain. So you can take cells 1 2 3 4 5 6 7 8 9 10 11 12. So these cells basically they are present inside the domain, they are not outside the domain. So edges A, B, C, D, so they are basically called the boundaries of the domain. Okay, so these boundaries, what they are doing actually, so these boundaries uh, they are actually containing or constraining the matter in it. So whatever the physics change will happen, it will happen inside. Now, when we compare this 1 and 2, so this 1 and 2, so one is what? A structured mesh, and other one is called unstructured mesh. Okay, so even though if you have same dimension, now what happened actually? So when you use unstructured mesh, the number of cells is going to increase. Okay, and number of points is going to increase actually. That is one thing. Now, if we compare 1 and 2, so the smallest entity, as I told you, so this is called a cell. Now, in the structure mesh, what is the shape of the cell? So, this is called a quadrilateral cell. So, this is 1. Now, take this same cell of 1 actually. Okay. So, take this as 1. Okay, so this is 1 which is of quadrilateral cell, fine, and this is again 1, so which is of triangular cell. Okay, so let's actually write here. So basically this one, let's say this is called tri, and again the same another thing, so this one is called quad. So triangular, quadrilateral, fine. So here, what is happening actually? So when you take unstructured mesh, so this is actually one more thing. It's 2D actually. So basically, it is 2D. This is 2D. There is no z-axis. So if you see clearly, so we have y-axis and we have x-axis. There is no z-axis. So since we have x-axis and y-axis, so it is called 2D. So therefore, for 2D mesh, so what is happening actually? So we have this cell which is of the basic unit or the smallest entity. So which is of 1, 2. So if you take a particular cell, so 1 is a basic entity, 2 is also a basic entity. So individual, I'm talking about individual. So 1, 2, 3, 4, all the cells when you combine together, so which is looped by, or let's say which is bounded by the edges A and B, is forming a domain and a mesh. Fine. So here, as I told you, so we have quadrilateral shell, so which is of 2D. So basically when I when you hear about basically triangular cell or quadrilateral cell, so you should be able to recall that. So it's a 2D mesh. Okay, so in any CFD problem, so people will define. So let's say any research paper or any work, CFD work, they'll mention about the mesh. So if they say the mesh is structured with triangular cells, or let's say it's a quadrilateral cells, so when they pronounce it as a triangular cell, so then you need to recall that it is a unstructured mesh of 2D. Okay, so triangular cells are only formed when you have a 2D actually. Fine. And next, when you go for the quad cells, okay, so again, if any research paper, if they mention that it is a structured mesh with a quad cells, so then you need to recall that it is a 2D. Okay, so here what is happening actually, so you take whatever 1 2 3 4 5 6 7 8 9 10 11 of structured, or 1 2 3 4 5 6 7 8 9 10 11 12 13 14 till 21 cells of unstructured mesh. So everywhere, so the flow physics is basically the same actually. So until unless the grid independent study is done. So as I told you, so when we recall, so grid independent study. So grid independent study in the sense grid independency or mesh independency study in the sense. So let's say we have how many grid points here. So we have grid points. So basically the grid points are formed section of X lines and Y lines. So here for the quadrilateral cell, so how many grid points we have? So we have grid point 1, grid point 2, grid point 3, grid point 4. So 4 grid points we have, okay, for a quad cell. But if you take triangle cell, so how many grid points we have? Grid point 1, grid point 2, grid point 3. So how many edges we have? We have edge 1, 2, 3. 3 edges. Here we have here it will be like 1, 2, 3. Here 1, 2, 3, 4. So we have 4 edges. So basically what is happening actually? So when you take the triangular element, we have 3 edges. When you take quadrilateral element, we have 4 edges actually. So irrespective, so whether it is a triangular element or the quadrilateral element, so when you have the mesh independent study, so when mesh independent study in the sense, so let's say for a given cell you have a 4 grid points. So if you take entire domain, let's say we have a grid points of let's say 1 2 3 1 2 3 4 5 1 so 5 15. So we have 15 grid points here for this mesh. So here it might be, let's say, into 3 45 grid points, let's say. So when you change, so one set of simulation, so let's say for M1, so which is called mesh 1, so let's say it has some 1 million grid points. Okay, so M2, let's say it has a 2 million grid points, and M3, let's say it has 0.5 million grid points. So it doesn't matter whether M1 has structured mesh or M1 has unstructured mesh. So it can be, so these things, so it can be structured or unstructured. Okay, so it can be structured or unstructured mesh. So what happens actually, so here we get results for M1. So for M1 mesh, let's say we have a velocity u is equal to 0.5 meter per second. Okay, so for M2 mesh, let's say you are getting a velocity of 0.5 0.09 meter per second. Okay, for M3 mesh, let's say you have a velocity of 0.481 meter per second. Let's say. Okay, so if you compare this one, what happens actually? So when you have more number of grid points, so where you have more number of grid points, we have M2. So M2 is a point it's a sector where you have more number of grid points. So when we have more number of grid points, we say that it is called a finer mesh. So finer mesh in the sense, so we have more number of grid points, and the cells are very closely tied, or let's say because the grid points are very nearby. Okay, so M1, so basically is called the medium level mesh. Fine, and M3 is called coarser mesh. Coarser in the sense, like let's say you have less number of grid points. Okay, and when you compare this M1, M2, and M3 mesh, so what is happening actually? So the error. So how do you find error actually? So the error of mesh in percentage will be equal to. So let's say this M2 is called finer mesh. So M2 minus M1 divided by M2 into 100. Okay. So here what is happening actually? So when we take this M1, okay, and M2 and M3, okay. So for this M1, M2, and M3, so we need to actually find the we need to find the value of the epsilon. So the epsilon, or let's say the error of mesh 1 with respect to 2. So mesh 1 with respect to 2. Okay, in percentage is equal to, so let's say you have M2 minus M1 divided by M2 into 100. Okay, this one we have. Next, what do we have? So epsilon M3 to M2. So in terms of percentage, which is equal to, so we have M2 minus M3 divided by M2 into 100. Okay. So what is this actually M2M? So here we have the velocity of M2, which is 0.509. So let's say we have M1 0.5. So now what is happening actually? So for this, so we get so let's say 0.509 minus 0.5 divided by 0.509 into 100. So what happens actually? So we have 0.009 divided by 0.509 into 100. Okay. So then what happens actually? So here the 2 so it's all about 0.9 divided by 0.509. Okay, so what is happening? So you have an value of the, or let's say error. So error approximately it becomes nearly 1.9, or let's say 1.8, some, or 1 point. So the error will be in between 1.8 to 1.9%. Okay, so this is what happening. The error, or the result error, or the result value error. So between this M2 and M1 is clearly seen here actually. Fine. So next we'll see for the between M2 and M3. So what is the value of M2? So which is 0.481. So next, so error between M3 and M2. So we have 0.509 minus 0.481 divided by 0.509 into 100. So now what is happening actually? So the value is approximately it's of 0 point 0.028. Sorry, we have 0.028. Yeah, so it is 0.028. So this 0.028 divided by 0.509 into 100. So therefore what happens? It's of 2.8 divided by 0.5. So approximately, so 280 by 5.09. So let's take it as 5.1. So it is becoming, let's say, nearly of 40%, or let's say in between the error of like, let's say 50% of error actually. Fine. So 40 to 50% of error. So when you compare, so this error between M2 and M3 and the error between M2 and M1. So what is happening? So the error of the result between M2 and M1 is less, and M2 and M3 is more. So therefore we will go with the mesh of M1. Why M1? Why not M2? So why not M2 actually? Why? Because when you take the more number of grid points, so let's say as we see here, so M1 we have 1 million grid points, and M2 we have, let's say 2 million grid points. So if we are solving a 2D equation, let's say this is a 2D problem for a 2D, let's say incompressible flow. So we have the flow as incompressible, let's say invisible. So we have, let us say this is a point 3. Okay. So at this point 3, so we have variables as P3, let's say U3, let's say V3. So density, if you take constant, then rho is constant. If you take it is inviscid, then mu is like 0. So that is one thing. So here P3, U3, V3. So is how many variables we have? We have nearly 3 variables. So these 3 variables are located at only one grid point. So imagine, so what is happening? So if we have 10 grid points, so how many variables are there? So total 3 into 10, 30 variables are there. So imagine, so we have 1 million grid points. So how many variables are present? So it is of, so let's say here, so let's go here. So here you can see this is of M1, which is of 1 million grid points, which is of M2, which has 2 million grid points. Fine. So here, if you take, again we'll draw a cell here. So let us take a point here. So this point is a point of interest, let's say. So at this point, let's say P, so or let's say this point, let us take it as 3. Okay. So you have the variables as U3, V3 and P3. So at all the grid points, you have the velocities, U velocity, V velocity and pressure. Okay. So I have how many points actually here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 grid points. So I have 15 grid points. Therefore 15 into 3, total 45 variables are present for this mesh. Okay. So how 45? Actually you have at the first grid point U1, V1, P1. At the second grid point you have U2, V2, P2. At the third grid point you have U3, V3, P3. Fourth grid point U4, P4, P4. Similarly at the 15th grid point, so we have U15, so U15, P15, P15. So it's like let's say U of P, V of P and P of P. So where P value is going from 1, 2, so on till 15. Similarly, what do we have actually? So if the number of grid points is going for 1 million, what happens actually? So you have U 1 million, V 1 million, P 1 million. So therefore, you have 3 million variables actually. Okay, that is for M1. Imagine, so you have 2 million grid points. Then what happens actually? So you have U 2 million, V 2 million, P 2 million. So it's of approximately 6 million grid points. At the end, the CFD process, so when you take this mesh, so already we have seen finite difference, we have seen finite volume method. So whatever method it is, whatever the grid points you have, let's say for all the grid points, so you take 1, 2, 3, 4. So let's so on these grid points, so we form, let's say, a matrix which is of A of X is equal to B actually. So A is nothing but the coefficients of these values. So U1, V1, P1 coefficients. This is called A is called coefficient matrix. So this X is a unit vector or a column matrix. So which you have, let's say U1, V1, P1, U2, V2, P2, U3, V3, P3, so on. So let's say if you have 1 million grid points, so let's say this is U 1 million, V 1 million, P 1 million. So that will be the size. So let's say how many, so the column vector size will be 3 million cross 1. Okay, so that is the size of the matrix. So what will be the size of the matrix A? So that will be 3 million cross 3 million. So the matrix size of B is, so that is also same 3 million cross 1 million. So to invert a matrix, so you can think for 2 by 2 it is very simple, 3 by 3 matrix it is simple, 4 by 4 let's say it is somewhat difficult, 5 by 5 it's somewhat difficult, 10 by 10 it's like difficult by solving by hand, we have to use programming, 100 by 100 it's also difficult. So when you go for 1 lakh cross 1 lakh, it is very very difficult. So to do one iteration, so one iteration in the sense, let's say you have X is equal to A inverse of B. Fine. So X is nothing but A inverse B. So this A inverse B is basically what happens is coefficient actually. So this A inverse B, if it is happening for one time, this is called one iteration. So one iteration in the sense one time inverse and B. So every time you need to update the value of X at each and every iteration. Okay. So this is what happens in the computational aerodynamics for each, whether you take a cell-centered cell at a node point or at the center of the cell. Fine, irrespective of that. Now, what is happening actually when you use structured mesh? So you have less number of grid points. You have let's say and complexity is less and easily solvable. When you take unstructured mesh, so unstructured mesh in the sense you have triangular cells. So triangular cells, so they are basically connected together with a large number of points. So you have large number of cells. So therefore, what is happening actually when they are joined together? So it is forming a domain with a large number of points. So large number of points in the sense you have very lengthy matrix of A, lengthy matrix of X, lengthy matrix of B. So it is time taking process to solve the simulation for unstructured mesh compared to structured. So as I shown in the slide here, so same 1 cross 1, same 1 cross 1. So if you take structured mesh, if you take unstructured mesh, so what is happening? So here you have more number of cells, more number of grid points. So therefore, the size of the matrix A is very high and the size of the matrix X is high. Fine. So this is what happens for the unstructured mesh. Okay. So this one we are talking for only till now it's 2D. So what about 3D actually? So we have seen about a triangular and we have seen about quad. Now, so we need to see about hexahedra and tetrahedra. Okay, so when you take, so this is called our tetrahedra. Fine. Now what is hexahedra? So this is called hexahedra. Okay. Now, where do we get this tetrahedra actually? So this tetrahedra cells will be obtained when you take this 2D unstructured mesh as a 3D. The 3D of the triangular unit is called the tetrahedra, and the 3D unit of the quadrilateral cell is called hexahedra. Fine. So here what is happening? The difference between 2D and 3D. Okay. So if you see this mesh, so if you see this mesh, so what happens actually? This is of 2D. When you take it as a 3D, so let us take the structured mesh. What happens? So previously we have this, let's say this as x-axis, y-axis, z-axis. So previously it was only 2D. These of x-axis and these of y-axis. Okay. So what is happening actually? So this is of 3D and this is of 2D. Fine. So in the 3D, what is happening? So we have layers along Z. So let's say for a given 2D layer, so we have a grid points of so we have a grid points of 15 or let's say 45. So this 45 into the Z-axis layer. So let's say Z-axis we have 5. So 45 into 5. So this will be the total number of grid points for the total entire 3D. Now for 2D what happens actually? We have only the 45 cells. So that is the difference between 2D and 3D. But in general, like nothing, it is 2D. So all the geometry, all the dimensions, they are of 3D nature, and the flow turbulence should exhibit 3D actually. So 2D simulation or the 2D cells or whatever it is, so they are for the initial uh, basis for the CAD simulations. Why? Because so you want to visualize the physics of the flow initially with some assumptions with the sample calculations. To go for that, what we do is like we take the 3D dimension in any view, front view or top view. So we will actually see those things in 2D or 3D. Fine. So when we take in 2D or 3D, so what is happening actually in 2D? So we are just assuming it as one plane, or let's say any plane which is of front view or which is of top view. Fine. So if you take it as front view, so what is happening actually? So the amount of physics that is captured will be of front view. If it of top view, that is of top view. But if you want to capture the entire physics of the actual dimension, so you have to go for 3D. Okay. So why? Because you have turbulence actually. So there is an entity called turbulence. So where the flow will move randomly from one place to other place. So it does not follow any direction, any rules or any regulations kind of thing. So if one fluid particle let's say if it is in this layer, so this fluid particle in the next time it will go to other layer actually. So the mixing of, let's say this is layer 1 and 2. So the layer 2 of fluid particle will come to layer 1, and then they exhibit this random nature. Okay, so this random nature exhibition is basically making the problem tedious actually. So here when you take 3D, so the amount of flow variables are getting increased. Okay, so why? Because here previously we have 45, that's of a very less number, but 45 into 5 is okay, somewhat larger number. But if you are increasing the physics of the flow, the amount of variables will increase. Let's say previously what we have U, V and P. So this is for what? Only incompressible flow. This is for only incompressible flow. Fine. Next, when you want flow as compressible, okay, and you have heat transfer, then you have a variable U, V, P, rho and T. And still it is 2D, it's not 3D. Remember that. Why? Because when you take 3D, so the velocity is U, comma, V, comma, W will be there. So which is of having a vector, which is having a combination vector of U. Okay. So, but here when the flow is compressible, what happens? You have 5 variables. Here you have 3 variables. Okay, let's exaggerate it. So we have a grid points, let's say of 250. 250 grid points. If you have 3 variables, you have into 3. You have variables. Let's say you have U velocity, V velocity, and P. So what happens? So this will go as 250 into 3 variables. This is one math. This is for what? Incompressible flow. Whereas if you go for compressible flow, let's say same 250. Here what is happening? So you have the flow variables which you have U, V, P, rho and T. So U, V, P, rho and T. Now this U, V, P, rho and T, what is happening actually? So they are forming 250 into 5 variables. These are what? Compressible flow. Okay, so that is the difference between incompressible and compressible flow. So when you have incompressible flow, the number of variables are decreasing. When you have compressible flow, the number of variables are increasing actually. Fine, for the CFD problem. Now let's actually, so basically this entire thing is what? For 2D only, not 3D. So when you go for 3D, what happens actually? One more variable will come into picture. So here you will have, for this thing, additionally you have W velocity. For this thing also you have additionally W velocity. Fine. So therefore what is happening actually here? So additionally you will get this as 4. Additionally you will get this as 6. So let's say for the 2D incompressible flow, let's say we have 250 into 3. Whereas for a compressible flow, what do you have? You have 250 into 4. So this is the count which will change for only 2D. Imagine when you are taking it as a 3D. So for 3D, in the sense, what do we have? So we have the cells. What are the cells? So basically you have tetrahedral cell, you have hexahedral cell. For let's say, let us think, let us compare here. So this is a 3D diagram and this is 2D diagram. For these 2D diagrams, how many grid points are required? So you have 1, we have 2, we have 3, we have 4. So for this, how many grid points are required? So we have 1, we have 2, we have 3, we have 4, 5, 6, 7, 8. So what happened actually? It has doubled it. Okay. Let's say it has only, let's say you have a unit cell extraction or extrusion. Okay. So we have a 2D mesh which is of 250 grid points. Let us assume for the 250 grid points. So for the 2D mesh, if you extrude it, it becomes 250 into 2, let's say double actually. So it becomes 500 only for unit y axis. So if we let's say if you make it this one for 3D, extrude it, so for only one unit z axis, how much? 1 unit z axis. So then what is happening actually? Then it becomes, so 500 into 4. This is for what? 3D. Okay. Next, again, so if you extrude again, it is as unit z axis. For the compressible flow, it becomes 500 into 6. Okay. So what is happening actually here? Because of extrusion, we have one more variable, and the points which we have, they are keep on increasing actually. Fine. So in general, so we can say that if you take 2D mesh, that physics is captured with assumption manner, and then for the 3D mesh, it is captured in realistic manner. And when you take it as a hexahedral cell, tetrahedral cell, and let's say hexahedral, tetrahedral. So hexahedra is for the 3D structured mesh, tetrahedra is for 3D unstructured mesh. And when you take structured mesh and unstructured mesh, so what is happening? For a structured mesh, we have like orthogonality very well, and when you have orthogonality very well, the errors associated with the CFD problem are less. So when you have non-orthogonality nature, we need to correct it. But the difference or the problem what happens when you take unstructured mesh, the more number of grid points are happening. So that's why in general, so when you want real physics, so then you need to go for the tetrahedra or hexahedra. But the problem when you compare between hexahedra and tetrahedra, what happens? For the hexahedra cells, so let's say 3A structured mesh, you have less number of grid points when you compare to tetrahedra cells. Okay? Why? Because for a given unstructured mesh, you will have more number of grid points and more number of cells. Okay? So this is what the basic differences or basic entities of triangular cell, quadrilateral, next you have hexahedral, and you have tetrahedral. Okay, so where we have seen the triangular as a 2D unit, quadrilateral as 2D unit for the structured meshes. Okay, for structured meshes, let's say a triangular. For structured meshes, the triangular unit will not be possible. The unstructured meshes, the triangular is possible. That is for 2D. Similarly, the 2D unstructured mesh can be extruded to 3D, so which is called tetrahedra. Okay. Next, we have a 2D structured mesh, so which is called quadrilateral. So the quadrilateral mesh of the 2D, when you are extruding along z-axis, we get a cell called hexahedra. Okay. So these are the basic information about the triangular, quad, tetrahedra, hexahedra cells of a given mesh. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.